Okay, well, Peter's sort of told you a wee bit about me, but let me start off by introducing myself. This is the first thing. I spent 39 years in the army. I left school at 16, and at the age of 55 they decided I was no longer fit enough to continue and retired me off. Of course, you don't spend 39 years doing the same thing all the way through. If we forget the first year and a bit where I sort of made a mistake, let's put it like that, and joined the wrong bit of the army, I then moved into Royal Signals as a technician. And so I see my background, you know, for the first half of my military career in telecommunications engineering. And then I was lucky enough to get a year off. When I say a year off, I mean I got a year at college paid for teacher training, and was commissioned into the educational corps after that year, which is where my first posting as an education officer, I had the privilege, and I do mean privilege, to teach junior soldiers just up the road here at the Bridge of Don for 3 years, from 78 to 81. And then, oops, too many. And then after I'd been an education officer for 9 years, I teaching various things, including a stint teaching maths and electronics, which was quite interesting. Then I was selected to go and read for a master's degree, and I read for the design of information systems with Cranfield, and so came into the IS part of the army. Initially looking at the use of computers in education and training, and then went off to a standard educational job. And then when I was about 49, I was looking for something to do, and I got a phone call, and it went like, the Army's setting up this new team to do data management for the Army, would you like to join it? Well, I thought I knew what data was, and I taught management, but I'd never heard the two words put together, but yeah, let's go for it. So I went for it. So for my last 6 years in the Army, I really spent my time in data management. First of all, as a member of that team, and then when I was selected for promotion, I spent the last 3 years in the Ministry of Defence as the staff officer responsible for data management strategy for the Army. And then when I left the Army, of course, I just carried on. I didn't want to go and work for anybody other than myself, so that's what I've done ever since, doing consultancy and training in principally data management, and continue to study and look into data and the way data is handled in organisations. And as a result of that, about 10 years ago, I was invited to join the ISO standards body that's looking at data management standards. So the subcommittee that I work in has 4 working groups. One of those is developing the SQL standard. The group that I'm in actually is developing standards for metadata and handling metadata. And then lastly, I think I put myself down as a big data skeptic. The last few years, you know, getting all these emails about big data and big data technologies and everything else. And it just worries me that the IT industry is very good at seeing a passing bandwagon and jumping on it. A few years ago it was XML. You know, we don't know what your problem is, but XML is the solution. I had a boss once who said, I don't know what your problem is, but Microsoft has the solution. So there's always, you know, this passing bandwagon, and I'm just worried that big data is the current one that everybody's trying to jump on. So there you go. But how did I get into big data? Two ways, really. One is, a few years back, I wrote a book for BCS on data management, principles of data management. And a year or so ago, they asked me to write or produce a second edition of that. So here I was in 2013, writing a book on data management. And I thought, well, I've got to mention big data, and I've got to mention NoSQL databases in that book somewhere. So I wrote a few pages on that, and then the SC32, the standards body, suddenly started looking into, can we produce standards for big data? So we had to understand big data within that body as well. So these things came together, and I started to look at big data. And then somebody in the publishing world knew that I'd done that and asked me to write an article for, on the special edition of IT Now that they were doing on big data, and it was to be a sort of top level article. So I wrote that article, that got published. Peter contacted me. Yeah, it was in there. Peter contacted me and said, will you come up to Aberdeen and talk on big data? And my first email back was, do you really want me to come and talk on big data? Do you really want me? Because I'm really worried about it. And yes, he said, you're the guy we want. So, okay, so here I am. It's me that you've got. Okay. So, but just 2 or 3 days ago, when I was putting this presentation together, I found this, and I love it. I'll just let you read it. I think that is so true. In some ways, in the IT industry, we are, although we talk about software engineering and everything else, we are really still at the cottage industry idea. People keep on coming up with ideas and new ideas, and they go off and they do their little bit, and everybody really tinkers around. And this warning, I think, here is that well, it just tickled me because, as I said, I'm a big data skeptic. Okay, so what do I get? My presentation is really broken down into 4 bits. First bit is defining big data. What is it? The second is storing big data, which is really about NoSQL databases. The third bit is using big data. And the 4th bit are a few final thoughts. So let's start off with defining big data. So towards the definition. Okay, story. 2 years ago, 2.5 years ago, there was an article in the New York Times, and my wife was sitting over there and said, you've got to read this, they're talking about big data. And what this article was saying, that there was a problem in New York. And the problem was lots of fat blocking the sewers. And there was one bit of the New York City Council which knew about where the sewers were and had data on the sewers. There was another department which had data on where all the restaurants were. there was another department which had data on the contractors who were going to restaurants to collect fat, used fat. Put that lot together and you could work out which restaurants didn't have contracts to collect their fat, which were closest to where the sewers were, and you probably found the culprit. And this was presented as a way of using big data and using the techniques of big data. My wife's comment, having read that article, was, it is only information. That's all they're talking about. It's making good use of the information that was available. Then I took myself off to, almost 2 years to the next month, I took myself off to a seminar on big data run by the IEC, and trying to find out what this was. And there were basically 5 presentations in this day. The first presentation was all about the government's Open Data Initiative. I'm not quite sure what that had to do with big data. The second presentation was from somebody who was in a scientific community, and they were going to, or they were planning to plant lots of radio telescopes in the desert, either in Australia or South Africa. And these radio telescopes would be collecting masses and masses of data, and they had to store it and at some stage analyze it. The second presentation was from somebody from a telecoms company. And the problem that they were wrestling with was that they could make money from, say, Chinese restaurants if you had been searching using your mobile phone for Chinese restaurants. In other words, you said that you like Chinese restaurants, so that when you are walking down the street and you're within 10 yards or 20 yards of a Chinese restaurant, they suddenly ping you with a message saying, hey, there's this Chinese restaurant here and they're really good. So in other words, for them, the important thing was the speed with which they could analyse and work on this data. And then the next presentation was all about somebody who was trying to bring lots of different types of data together, some of it structured, some of it unstructured, and so on. And then the fifth presentation was from a lawyer. But nowhere did they actually define what they meant by big data. There was just this series of presentations all talking about different things. And I must admit that I left that presentation totally confused. Did not understand, nowhere had they sort of pulled that together. And then I read on a bit. And I found out about Gartner's 3 V's. And I don't know if you know about Gartner's 3 V's, but what they say is that what we're trying to deal with is, with big data, it's either data that is high volume, so we're talking about from terabytes to zettabytes of data, large quantities of data, or they're talking about velocity, so where you're going from batch to actually trying to, whilst data is coming at you, you're trying to make use of it, or variety, where we've got from structured to through semi-structured, such as an XML document or a JSON document, through to totally unstructured data. So that was Gartner's 3 V's for trying to make sense of the big data and what big data is. And just to show that that's got somewhere. Here's a graphic. I was, as part of the standards work, I was in Beijing in June, and we had a whole day talking about big data in Beijing. Lots of presentations from Chinese and ourselves. And this is a graphic that I collected, you know, out of that presentation from one of the Chinese presenters. So this idea of the 3 V's has become very common in trying to understand big data. But in the work that we've been doing in the standards world, we thought that those 3 V's didn't go far enough. And so we've got the 3 V's, the volume, the variety, and the velocity. But then we've added to them, and we've added value. We think that value is something that's actually quite important. There is no point in collecting data if it doesn't add value to the organisation. So we think veracity is important as well. So, you know, we're looking for words that begin with V. But veracity, so where the correctness, the data quality, if you like, can be guaranteed, you need as well. And variability, where the change in velocity is important to the organisation. So we've gone on and we've added those. And we've actually, when I say we, my colleagues, as I sort of step back at this stage, have come up with a definition of big data. And here it is. So big data is a data set with characteristics, for example, volume, velocity, variety, variability, veracity, etc., that for a particular problem domain at a given point in time cannot be efficiently processed using the current existing established traditional technologies and techniques in order to extract value. So what we're really talking about is our traditional databases don't cope, basically. That's what we're talking about. So this goes on to say that the definition distinguishes big data from business intelligence from traditional transactional processing, while alluding to a broad spectrum of applications that includes them. The ultimate goal of processing big data is to derive differential value that can be trusted because the underlying data can be trusted. And that comes out of the study group on big data, and that has not, I'm not sure that this has not been published, okay? But it's a
draft, definitely.
Yeah, well, it's an internal report, yeah. So we have a definition of big data. So what about storing big data? Well, part of that definition said we can't store it with traditional means. So traditional means for most people means SQL databases. So let's start thinking about SQL databases. An SQL database is based on the relational model of data. As such, it is grounded in mathematical set theory. It's mature, it's well understood. In fact, it's so well understood that most people, if you talk to them about a database, they can only think in terms of SQL tables and columns, and they can't think of anything else other than that. It provides concurrency support and transaction support. So transactions are seen as ACID transactions, atomic, consistent, isolated and durable. So a transaction, either everything happens or nothing happens when it's stored. have a fixed schema. What do we mean by that? Well, basically, before you can store any data, you have to define the tables and columns in which you're going to store the data. And now SQL is now object relational. It has grown so much. The SQL standard, one of the guys I work with was saying, you know, when we the first standard was 40 pages long. SQL then grew to about 400 pages, and now, and this was 3 years ago, it's 4,000 pages, and it's getting larger. So there's so much now going into the SQL standard that it's gone beyond what most people think of as pure SQL. But it has problems. The first one is that because it's based on set theory, every time you query the database, what you get back is a set. But your programming languages aren't looking for a set. They're looking for an actual value. So there's what is called an impedance mismatch between our databases and our programming languages that we use to program the database. That may or may not be a problem. Relational databases don't scale well. Despite the advances in the standard, the principal SQL databases that are available on the market are quite old technology. And the database engines are still, despite the fact with the object relational you can have quite complex data types, so you can hold quite a complex concept at a row-column intersection. The technology that underlying that is still only really expects to see short numbers or short character strings or so on. They have to fiddle the technology to make it handle these new types. And an SQL database was never designed to hold the quantities of data that are out there today. And basically, if your data outgrows your box with your SQL database, what you have to do is go out and buy a new box and move the data to the new box. What you generally can't do is bring a box alongside it and put some of the data in that box and some in that one and manage them as a whole. It doesn't work. And they're very poor at handling semi-structured and unstructured data. There's a part of the SQL standard now, SQL XML, and it's got an XML data type in it. So that means that a row-column intersection, you can hold an XML document. That's all you can do. You can just hold an XML document and know that it's an XML document. You can't search it or do anything with it. So it's not much, I would say that it's not much use, but there are other bits of that SQL XML that allows you to take things out of tables and create XML documents, and take XML documents and put them into tables. But the XML data type itself just says, here is an XML document. And the other thing about SQL databases is they can't really handle new data types. Well, the object relational bit is the structured, user-defined data type, the structured data type, so you can make complex data types, but actually the attributes in that data type all have to be of types that SQL can already handle. So they have to be strings, integers, and so on. So trying to develop or think of new data types is very difficult. So there's a problem, or a perceived problem, with SQL databases. So the solution is no SQL databases. Now, what does no SQL mean? It depends who you talk to. In some cases they're saying not only SQL, so there's SQL underlying it and they're expanding it. Or in some cases it's never ever SQL. I don't want to know SQL. I don't want any standards. I just want to do my own thing with the data and go away. But no SQL databases, there were, last time I checked, over 150 no SQL databases on the market, all doing something slightly different, all for their own little piece of the market. One thing about them all is that they are schema-less. So in other words, what they're saying is that you do not have to define what data you're going to store in the database beforehand. You can store any data in the database. We worry about how we query it later. You store anything, worry about it later. They're scalable. They're designed to be scalable. They're designed to work well in clusters. So when your data fills your box, you get another box and you put it beside it and you run them together, or you and so on, and you build up and you build up and you build up. And they basically fall into 4 basic categories, which are key value stores, document stores, what are called wide column or column family stores, and graph databases. Now, those are broad categories, and some actual databases have a bit of this and a bit of that and so on. But what I'll do now is look at each of those in turn and see what the underlying concept is. Key value store is very simple. There's a key on the left, and on the right we're storing some data, and we're actually saying what that data is as we store it. So we've got a key on the left and we've got the values on the right. And you can see that what we're storing as the value in the top row is totally different to what we're storing as the, well, not totally different, but is different to what we're storing in the bottom row, the value there. And products such as React and Redis are key value stores. Very simple, the simplest form of NoSQL database. Document stores is where we store documents. What do we mean by a document? Well, it's semi-structured, so it could be XML. It could be JSON, the JavaScript object notation. And so here we've got two customer records somewhere, and somewhere else we've got 2 order records. And in a relational database, you link those 2 together through the primary key, foreign key relationship. Not here, it's just done in the programming languages, recognizing that there's a value there that corresponds to a value somewhere else. So there's no integrity controls, there's no control over anything. You just store whatever you like, basically. And, you know, MongoDB, which is really one of the big sellers in the NoSQL market, CouchDB, are examples of document stores. Wide column stores are Yeah, wide column stores are key value stores, but there can be many values for the key. So, for instance, here we've got the key down the left-hand side and the columns across the right, but you see that there's different data in the width of the columns is different. Some of the real big players, like HBase, Hadoop, and Cassandra, which are the real big ones, and Hadoop, for instance, came out of the work that was done in Google to start with, for Google to handle its massive amount of data. Wide column stores. And the last one are graph databases, which really are what they say. They're nodes and there are links between them. And so this really does, I mean, this ties in very much with, I don't know if any of you know about this, but the work on the semantic web and the linked data and RDF triples and things like that, very closely related to the graph database. And there are Neo4j and SOMES are again 2 examples. But as I said, there are over 150 NoSQL databases. So, you know, what goes where is actually quite difficult. And performance comparison. If we take a relational database as an example, the variable performance, variable scalability depending on the actual product, very low flexibility, moderate complexity, key value stores, high on performance, high on scalability, high on flexibility, no complexity whatsoever, store anything. Document store, high variable, high, low complexity. Wide column store again, high, moderate flexibility, low complexity. But the graph database has high complexity. Just a sort of comparison between the different types. And if I set that on a graph, the key value store is where we've got the greatest quantity of data and the least complexity. Document stores about there, the wide column stores there, graph database is there. But the key thing is that 90% of the requirements for data and data storage, 90% exist below that level. So you really, when we're talking about big data and big data technologies, we're talking about just 10% of the, at the most, of handling the data requirements of the world. Excuse me.
Sorry, can you just clarify that one? Are you saying that most data is still really relational in tables, or are you saying that most data is just pure streams and you've got nothing else to it?
No, I'm saying, I think what I'm saying is the traditional data, most of the data requirements, 90% of the requirements that exist in the world today can be handled by traditional technology, which basically means SQL databases.
Yeah, and the data naturally has this characteristic of having multiple attributes, and that makes it easy to index and everything else. I just wanted to make sure I understood what your point was.
Using big data. How am I doing for time?
Well, you've got about 25 minutes and then we can open it up for questions.
I'm not going to talk for another 25 minutes.
All right, that's good. We want to schedule.
Okay. Obviously been talking too fast. Okay. Using big data. Right. So, I've already mentioned Google was in there. Google, the thing about Google, they have requirements. Their requirements are masses of data as Google has grown. They've got masses of data. What is that data like? Is it all structured data? No, they're into maps. So Google Maps, there's images. You do a Google search now, you get lots of images come up as a result of the search, which you weren't getting, a few years back on a Google search. How they manage that? Well, they went off and they designed their own database. They designed their own database. The relational technology wouldn't work. They wanted something that was scalable. They wanted to do their own thing. And so they created something called Bigtable. And Bigtable, somebody took that away, and effectively that Bigtable became Hadoop when it was productized. Amazon again. What about their data requirements? I mean, Amazon's trying to rule the world. They've got, wherever you go, there's an Amazon.fr, Amazon.jp, Amazon. All around the world, they're there. So they've got masses of data. What does it look like? Well, yes, there's your orders that you order, but there's the links that you do as the customer for data. Oh, that's a good book. I'll tag that as a good detective story, and other people will find it. So for that sort of thing, they probably need a graph database. But then there's the images as well. So, that you get all the... You don't just get a description of the product, you get the image of the product that you want to buy. So that Amazon, how do they handle that? They went out, they built their own database. The technology people at Amazon, SQL didn't work for them, they went out, developed their own database. That since has been productized. And then there's our old friend Facebook. Facebook's got, again, lots of linkages. This person's a friend with them, who's a friend with somebody else, and so on. The relational stuff for them didn't work, so they go off and design their own. So these were the big players, and you can... and what have they got in common? They're big. That's what they've got in common. They are big, and they're global. And then following closely along behind in the last few years, we found out are the National Security Agency and in this country GCHQ. And they claim that they trust us, we're being good guys, we're only storing metadata. Well, they're not. What is one person's metadata is another person's data, and I think they're storing data. But what they're storing is about every email and every telephone conversation that you had with other people, who that email's from, who it's to, what the subject was, and so on. All the phone calls that you make. They are storing that. The only thing that's letting them store that is the technologies that we've just been talking about, because the quantity of data that they were trying to store, they just couldn't have stored before on the relational structures. So what have we got? Well, with key values stores, remember they're the simplest ones. That's the simplest type of NoSQL database. So any session information, when you logged on, when you logged off, that sort of stuff. On web sessions that you might have, key value stores are good for storing that. Any user profiles or preferences, because they can change and so on, and there's no actual, probably no structure to that, so key value stores are good for that. Shopping basket, trolley information on the web, key value stores are good for storing that sort of information. But if you want to know the relationship between this piece of data and that piece of data, they are absolutely useless. They just do not handle that sort of thing. And anything where there might be lots of operations involved in a transaction, again, they're not very good. And so, and again, so with NoSQL databases, you're really picking the appropriate database for what you need. And the other thing that key value stores are no good at is if you run one query and you've got the answer as data, then using that data again in another query, which, you know, with SQL you can do very well, but can't do with key value stores. Document stores, login events, what happened when and so on. I mean, when I was doing data management for the Army, what I was very interested in was command and control. And the Army's command and control system back in the 90s, early 90s, was very rudimentary. The communication system was voice radio, basically. The database was handwritten logs. And the computational power was the human brain. And what we were trying to do was replace that with an IT system. Scary. Because it had to be the point about the voice radio, the handwritten logs, and the human brain, it was totally flexible. And, you know, if this thing had been around about then, I might have just thought that this was interesting. Content management systems. So, you know, the librarians are very interested in, and there's a document, could be electronic or it could be a physical book, and they want to know things about it. Again, the document store is very good for handling that sort of information, because what you want to know about this electronic document might be slightly different to what you want to know about this book, which you might want to know about this museum object, for instance. Any real-time analytics they're good for. Very good for e-commerce. So ordering stuff over the internet, you know, from one business to another business to business work. Very good for that sort of thing. But again, complex transactions, they fall down. And querying against aggregates which are constantly varying, then life gets very difficult. Wide column stores, again, event logging, they work, content management systems, so good. Counters, particularly, you know, in a web application, who was it? You told me that 51 people had seen on YouTube, seen the last presentation that you recorded. The event counter could probably, almost certainly, going to be a wide column store. Very good for handling that. Not suitable anywhere, but none of them are really suitable where you need ACID transactions. Okay, and the graph database is, of course, anywhere where you've got connected data. So friends, friend of a friend, and so on, employees, anywhere where you've got connected data or where you're into routine dispatch, the old, you know, how are we going to get from here to there to there? Or recommendations, as I said, when you go on to Amazon, you recommend, you tag a book as being good or something like that.
So do you assume Facebook is using Graph Database?
I don't know, but I would assume it is underlying there. It's not suitable for multiple updates. So I think actually, you know, there's a difference in the way you think in the life cycle. So in the relational paradigm, SQL databases, you collect the data, you prepare it, you then store it, you analyze it, and you take action based on that analysis. In the big data world, things are different. If it's a volume use case that you're interested in, you collect it, you store it at that stage without doing anything with it. You store it, the data, in its raw state. Then you prepare it so that you can analyze it and take action. If you're in a velocity use case, so you know, like the telecoms business that I was talking about, you collect the data, you prepare it, you analyze it, you take action, then you store it. So the way you handle, so it's not only the way you think about data, it's not only the way you store data, it's actually when you store it, you know, all changes. The whole world's up for grabs. And then I can't have a presentation on big data or big data and the NoSQL databases without talking about this thing called MapReduce, which is, I've read, is Google's greatest lasting contribution to computer science, whether that's true or not. Anyway, the idea of MapReduce is that if you've got lots and lots of data spread over different nodes, and you want to know, for instance, what's my total sales, then what you do is you map it and gradually you reduce it and reduce it, so you do it in little bits, and eventually you end up with the total up there. It's just a way of handling data. So that's really all I wanted to say on using big data. And the final thoughts are final thoughts. Here's the first one. So here we are. I finally replaced my Postgres server with a NoSQL solution. So you scrap 40 years of industry experience for what? Now I can web scale to over 10,000 nodes. Cool. How many customers do you actually have? Counting you and my mum, 2. Okay, and there's a quote there. And then from the same stable, it's not in the book, but having found that cartoon in the book, I then went and Googled the name and I found this one. So, are you Google? Yes. Are you using HBase? No. What about Facebook? Yes, also using HBase. No. Do you have a social graph? Yes. Are you Twitter? No. Do you need high availability? If you're Twitter, Yes, FlopDB. So FlopDB is the database that the Twitter's technical people developed. Okay, and I'm not sure if that's been productized and is available. But if not, then and you need a graph, then use Neo4j. Do you need high availability? Then key value store React. Use your data standard. Yes. Do you need web scale? No. Is it embedded? So on. So Couch and Mongo are two NoSQL databases. This is the bit I really like at the end. Do you need web scale? No. Use an RDBMS. Yes. No, you don't. Use an RDBMS. And the last thought is really, do not try to solve a problem that you don't actually have. Do not, if you're in a position where you don't have the use case to use one of the NoSQL databases, which are really there for that 10% of the problems that can't be handled by relational. Don't be bamboozled by a salesman into buying into a product that you don't want. And that's really my final thought. And that's me.